Hello, and welcome to the channel. Thank you so much for clicking on this week's video. Today, we will look at an optimization problem and use our knowledge of Sudoku puzzles to help us solve it. Alright, let's take a quick look at an optimization problem. No need to fret, we're not going to worry about solving it just yet. Hey, that rhymed! Okay, here we go. Example. A farmer wants to build a rectangular fence for his crops, with one boundary provided by a straight section of river. He has enough barbed wire to build 120 feet of fencing. What are the dimensions of the rectangle, length L, width W, which yield the largest possible area for the crops? Wait, what? Where do we even begin? Doing an optimization problem is just like doing a Sudoku puzzle. For instance, take a look at this 3x3 square. The way to solve this puzzle is to fill in each row and column with exactly one of each number, 1, 2, and 3. But in this analogy, let's say our main goal is to find the value of the bottom middle square. This is analogous to the goal of finding the optimal values in our example. Also, the givens are the two squares which already have values. These are analogous to the givens of the farmer's desired fence structure and the amount of barbed wire that he has. As it stands right now, there's seemingly nothing preventing the goal square from having any of the values 1, 2, or 3. So right away, this seems very confusing and maybe even impossible, since the board is nearly empty. It's easy to get overwhelmed, but there's a simple way to conquer this puzzle. It might sound counterintuitive, but we actually don't want to focus on finding the answer to the problem, at least not yet. Instead, we should focus on filling in as much of the board as we possibly can. These are called the easy details. For instance, we see that this square has to have value 2, since the 1 to the left and the 3 beneath it prevents it from being either of those numbers. Similarly, this square has to have value 2 as well. Next, we find where there are 2 3s and 2 1s. Piece by piece, we fill in the squares that we know and find that the puzzle seems smaller and smaller. After filling in these easy details, we see that the puzzle isn't nearly as challenging as it first seemed. Now, let's go back to our optimization example and see if we can solve it. Alright, so a farmer wants to build a rectangular fence for his crops, with one boundary provided by a straight section of river. He has enough barbed wire to build 120 feet of fencing. What are the dimensions of the rectangle, length L, width W, which yield the largest possible area for the crops? Just like the Sudoku puzzle, this seems really hard, like, how am I supposed to find that hard? But don't worry about finding the answer. Let's just focus on filling in everything that we do know first. That is, let's identify our givens and fill in all of the easy details. Also, a picture helps a lot. We know that we need to draw a rectangle, with one side given by a river, and the other side is given by barbed wire. We should label the picture completely. Let's call the length L and the width W. We know that in total, there is 120 feet of fencing material, but we also know that the amount of fencing is given by W plus L plus W. That is 2W plus L. So, 120 equals 2W plus L, or rather, 120 minus 2W equals quantity 2W plus L minus 2W, and that's equal to L. Note that we're leaving off units until the very end of the problem. This will just save a little bit of time and a little bit of our paper. Now, we know that the area of the rectangle is given by A equals L times W. That is quantity 120 minus 2W times W. And that is 120W minus 2W squared. So, we can write the area as a function of W. Namely, A of W is equal to 120W minus 2W squared. Is there anything else we know? I'm not sure. So, it looks like we have filled in all of our easy details. Now is where the fun begins. We must identify our goal in this example. What are the dimensions of the rectangle length L with W, which yield the largest possible area for the crops? Well, the rate of change of the area is given by its first derivative. So we should look for local maximums of A prime of W. To do this, we compute A prime of W and set it equal to 0, because this will locate our potential local maximums, or minimums. A prime of W is the first derivative of 120W minus 2W squared. Of course, we know that the first derivative splits over sums or differences. So this is really the derivative of 120W minus the derivative of 2W squared. And by the power rule, we know this is 120 minus 4W. Now, 0 set equal to A prime of W, that is equal to 120 minus 4W, shows us that 4W is equal to 0 plus 4W, which is equal to quantity 120 minus 4W plus 4W, and this in turn is equal to 120. Therefore, W is equal to 4W divided by 4, which is equal to 120 divided by 4, which is equal to 30. Does this W give us a maximum? We can actually check this by taking the second derivative of AW and then plugging in W equal to 30. The second derivative of AW is equal to the derivative of the first derivative of AW, which is equal to the derivative of 120 minus 4W, that is the derivative of 120 minus the derivative of 4W, which is equal to 0 minus 4, that is negative 4. So we don't even have to plug in the value W equal to 30. We already find that the second derivative of AW is negative. Well, that means we have a frowny face, and therefore a local maximum. Is this a global maximum? Yes, because the smallest value for W of 0 feet will yield 0 foot squared area, as will the largest possible value of W of 120 feet, for then the length would be 0. Therefore, 30 feet is our global maximum. So, what is our true answer? Well, given this W of 30 feet, we find that L equals 120 minus 2W equals 120 minus 2 times 30, which is equal to 120 minus 60, that is 60 feet. Therefore, our true answer is open parentheses L, comma, W, close parentheses, equals open parentheses 60 feet, comma, 30 feet, close parentheses. Here, the parentheses and comma are important because they help tell us what order the length and the width are in. Now, as a bonus, we can find the maximized area by these dimensions. In particular, length times width, or 60 feet times 30 feet, which is 1,800 squared feet. And that's it for today. Math, just like anything else in life, gets easier the more you see it. Take, for example, your favorite movie. I bet you could watch it for the 64th time and still find some new Easter egg in it. For me, this is because I already know what to expect from the movie, so my eyes might wander to the finer details in the film, like by wandering to the posters on the wall, or the characters in the background. Now that you've seen this video, n times, see if you can fill in any gaps by watching it n+1 times. You might be surprised to find that it makes more sense. If you have any questions, be sure to leave a comment down below, and I'll be able to give you my take on it. If you found this video helpful or interesting, be sure to give it a like, as it helps support this channel. New videos are posted every Tuesday at 8 p.m. Eastern Time. To never miss out, be sure to subscribe and hit the notification bell. Thank you so much for checking out this week's video. See you Tuesday!